Hello. In our last video, we talked about the idea that the current into a node has to equal to the current out of a node. This is formalized in something called Kirchoff's current law, and it helps us to do things like solve for unknown currents in a circuit. Formally, Kirchoff's current law says the sum of all current into a node must equal the sum of all currents out. This is a direct consequence of the law of conservation of matter. Any electron that goes into something must come back out. I can't create them or destroy them. Mathematically, we might say the sum from k equals 1 to n, ik, where this represents current in, has to equal to the sum from j equals 1 to m, ij, and this would be current out. Very frequently, though, in a circuit, you don't have that many connections to worry about. This notation is great when you have a lot of connections. However, when you don't, it's a lot easier to just write down equations for each node about which currents are going in and which currents are going out. I'm going to show you an example right now where we can do that. I'm going to be using the circuit from the last video. Example. So in the circuit below, what is I for? Let's draw that circuit. Now, we can't answer this question yet because we don't know any of the other currents. We can find these in many different ways, but for now I'm just going to tell you what they are. Let's pretend that this current here is 3 amps. Remember, I'd called that one I1. It's the current flowing through element number 1. Let's now also say that the current flowing this way is 4 amps. And remember that I called that one I3. When I drew it last time, I said that I4 goes this way. This is the first time that we're going to see what happens when we make that assumption, and it's actually the other way. It's not really that big a deal, but it's important to know that since I don't actually know which direction it goes, I am allowed to choose a direction arbitrarily, as long as I fix it in the end if I'm incorrect. So, by Kirchoff's current law, I know, let's just leave that up there a bit, that I1 coming in has to equal to I3 plus I4 going out. I can now plug in the numbers that I know. I know that I1 is 3 amps. I know that I3 is 4 amps. Plugging them in, and solving. Now I get a negative. What that means isn't really anything big. It's that I didn't know the real direction the current was flowing. It was in fact going the opposite direction. So in this diagram, I assumed it was flowing from the left to the right. It's incorrect. It's actually flowing from the right to the left. So I can redraw my diagram and label all of my currents. So I1 doesn't change. It's going the same direction. I3 doesn't change. It's going the same direction. I4, however, does in fact change. It's going this way. And now it is positive 1 amp. Remember, I flipped the arrow, so I flipped the sign. I have to stay consistent. In this course, I've said this before, we prefer to work with positive numbers. If you want to work with a negative current, that's also fine. It doesn't really matter. A negative current to you just means a positive current to me going the other way. As long as we can agree on that, then all of our answers will agree in the end. So that was Kirchoff's current law. In the next video, we're going to look at something called Kirchoff's voltage law. However, before we can do that, we have to understand the question of what does it mean to have voltage in a whole circuit. We've already dealt with voltage in an element, but now what happens in a whole circuit? And that'll be the focus of the next video. Thank you.